for the introduction, and thank you, the organizers, for the invitation to this beautiful place. It's my first time in Natal, and I hope to come back. So today I'm going to talk about what is called the Yu-Shiba impurity, that is essentially a magnetic impurity on top of a superconductor, and it's an old problem that was studied in the 60s, and in the 90s there were some experiments. And from the point of view of, or with the idea in mind of using it for quantum computation. And in other words, we'll try to see whether we can catch some sort of Majorana fermions from this type of model. In this talk, I'm not going to tell you the full story, but just to pick a very simple model and try to show you how to deal with it from the technical point of view. It's the talk is rather big technical with a rather long introduction, but so we always have in mind these sort of applications to Majorana fermions and quantum computing. So let me just a few words about this picture. This is our new building in La Plata. We just moved 2 months ago, and we must say that it's a very nice building, and hope you can visit it sometime. Okay, so let me tell you about my collaborators. Alejandro Lobos is from University of Cuyo in Mendoza. I have 2 PhD students that essentially made this most of this work with us, and Tomás Bortolín and Javier Feijó. And we have a long-term collaboration with these two people from the University of Cincinnati, Carlos Bolek and Naina Shah. Okay, so maybe this is a bit too introductory, but since I think the audience is quite heterogeneous, I prefer to do it. So some time ago, there appeared this very nice paper by Frank Wilczek, where he discussed the current status of the observation of Majorana fermions. So essentially, Majorana fermions are real solutions of the Dirac equation, which is a complex equation. So in principle, soon after the Dirac equation appeared in beginning of the century, Majorana asked whether there were some real solutions. He found them and started to think whether there were some particles that could behave as a Majorana fermion. At that time, he thought the neutrino might behave as that, but later it was proved that it would not be possible, because the Majorana fermion is essentially the same. The particle is the same as the antiparticle, and so the neutrino has its own antiparticle, so it cannot be the case. So up to now, there are no observations of such a particle. It might be possible that some theories of dark matter or supersymmetric string theories could lead to these Majorana fermions, but it hasn't been observed up to now. So it appeared the possibility of observing these quasi-particles or quasi-particles in condensed matter physics, more precisely in topological superconductors, as I will tell you in a moment. So what is nice is that, I don't know if it's nice, but the story of Majorana is quite sad. Soon after he discovered he made the proposal of this real particle, he just took a boat in Genova and disappeared, and nobody knew anything about him anymore. So some guys think he went to Argentina, but that's not verified. Okay, so a little more about Majorana fermions. So they are their own antiparticle. they obey an algebra that is totally different from the Dirac algebra. Essentially, the particle square is 1, whereas the Dirac fermion square is 0 as a result of the exclusion principle. And the commutators are essentially also different because of this factor 2. Of course, since these are real objects, one can always decompose a Dirac fermion in its real and imaginary part, and they turn out to be Majorana fermions. Another important thing is that if one picks a very simple Hamiltonian that essentially represents a single fermion, one can, using this decomposition, write it in this form. So always the Majorana of type I and the Majorana of type B they are always coupled. So essentially they are always in pairs. So the proposal for observing these particles in condensed matter was formulated by Kitaev some years ago. So he essentially proposed a very simple model, a toy model, where you have a fermion, a spinless fermion, a Hoping term, a chemical potential term, and a pairing term, very simple pairing term. And so the physics of this model, I mean, you can think about it as a chain of fermions where that can hope and that are linked also by the pairing term. And we can think of the chemical potential as an object that links the fermions with themselves. Okay? So if we decompose each fermion in its Majorana components, then we can think this lattice as a different object. We can put all the fermions of type A and all the fermions of type B, and essentially the Hoping and the pairing will couple the fermions of type A with the fermions of type B, but at different sites. So these yellow lines over here, we should have another lines over there, but at some point we can make them to disappear. I will tell you about that. So, and the chemical potential essentially couples the Majorana fermions at the same site. So we see what happened here. If for some reason we manage to make the missing lines here disappear and put the chemical potential to 0, then or is very low, then okay. Then we will form links or fermions in different sites will attract and or will form pairs, and these two fermions over there will essentially be on pair modes. So on the contrary, the other way around, if mu is large, then the pairing will be produced in this way, and the Majorana fermions in the ends will not be there. Okay, so this is they are exactly these two guys in the ends are exactly decoupled from the rest of the chain. In the very special case of mu equals 0 and delta equal minus t. In other cases, they are very weakly coupled, and essentially they will appear as some kind of border state which decays exponentially. So these two fermions here will give rise to a zero energy state, and actually doubly degenerate zero energy state that is exactly degenerate if the overlap of the fermion in this den is essentially 0 with the other one. So it depends. It decreases exponentially with the length of the chain. Okay. So why this is sometimes referred as a topological object? Okay, so I can always write my Hamiltonian in this way, where in the Fourier space, where D is this vector, 3D vector, that in this particular case of this model takes this form, but in principle it can be generalized and incorporate also other these Pauli matrices. These are Pauli matrices, and even some term that is proportional to the identity, but this is not important in my case. So essentially, this is the dispersion that one can compute immediately. And we see that this vector is always different from 0. We cannot make 0 all the terms at the same time. And essentially, it's a topological object because one can establish a map between the Brillouin zone, that is essentially, okay, the region of K between 0 and pi, and the unit sphere, okay? So this is half of the unit of the Brillouin zone because there are some symmetries that allow us to just concentrate on half of it. So essentially, we have two possibilities. If we see the extremes of the Brillouin zone, then the set component at the extremes takes these two different values, and it depends on whether T and mu are such that these objects are positive or negative. Then essentially I can have path of this way that starts from one pole and come back to the same pole, or starts from one pole and go to the opposite pole, and these are two different objects that cannot be connected by some soft or smooth variation of the parameters. Okay, so how to observe these Majorana fermions? There were some proposals in 2010 by these people. So the idea was to build some wire, semiconductor wire, on top of an S-wave superconductor. Then superconductivity is induced in the wire by proximity effect, and to add strong spin-orbit interaction and strong Zeeman field to it. And then the dispersion relation essentially will give rise to this dispersion that is like the one expects to observe Majorana fermions. So there were some experiments that try to build this object, and essentially one that was an early experiment and was this paper where they measure essentially the differential conductance and observe a zero bias anomaly. Since this Majorana state is at zero energy, essentially we can have conduction without bias, a peak zero bias peak. So the problem with that is that there are many things that lead to a zero bias peak. Even Kondo effect can lead to a zero bias peak. So this is nice, but it's not the smoking gun of Majorana fermion. So more recent experiments like this one try to build a quite similar setup, but to play with Coulomb blockade effect. The system is very, very small. They call it Majorana islands, and try to play with Coulomb blockade effect. And so essentially they have very nice results where they see whether there is a zero bias peak or not, depending on the parity of the electrons. And so that's what one expects, because this depending on whether these Majorana end states are populated or unpopulated. Okay, so but the issue of how to observe these states is not totally, let's say, settled, and so people keeps making proposals and trying to see whether there's a more direct observation of them. One of the proposals is this one. So it's essentially the idea is to use some bulk, superconducting bulk, and put on it some ferromagnetic impurities by means of an STM. And so they made the experiments, and they also observed a zero bias anomaly peak that you can see over here. This is the differential conductance, and you see that at zero energy, essentially there is a peak that is located in the end of the chain. So this is also a very nice experiment about it. So, but then here is the point at which I wanted to come. The problem of analyzing impurities in a superconducting background comes back and stands as a possibility for studying it. So the original problem and the one I want to recreate by other calculation techniques is the problem, the so-called Yu-Shiba-Rusinov problem solved by these people here in the 60s. So essentially, it is a Hamiltonian that has kinetic energy, a pairing term. Of course, we will take here an S-wave superconductor, and that also has a Kondo-like term coupling the spin, the electronic spin at a single point, and this is the origin, with a magnetic localized impurity. So this problem was solved by these people in a very specific limit, and so they consider the classical spin. So they took the limit of the Kondo coupling very small and the spin very large, and essentially so that the product is constant, and this essentially represents the classical spin. Analogously, one can say, okay, I just will keep the Z term here, or the parallel term, and neglect the perpendicular component, and this is more the point of view we will adopt in this work. So the solution of Shiba was possible because, after all, this is something that is quadratic, and with the localized impurity, if it is classic, it can be thought as a localized magnetic field. So they can use the analogous of the Dyson equation for the Green function, and essentially the T matrix can be computed exactly, and one has to plug here the BCS Green function that takes this form. So the result is that from the poles of the T matrix, one can extract the energy of the states, and in what the main result of this problem is that as a new state appear inside the gap, the superconducting gap. So there is a state of energy epsilon 0 that takes this precise form, where alpha here is this quantity J, S pi, and 0, where n 0 is the density of states at the Fermi energy. And this can be written as the tangent of the S-wave phase shift of scattering of electrons through the impurity. So the wave function is localized around the impurity and takes this form. There is an exponential decay where this the decaying length is given by this expression here. So this is the phase shift, and it appears in the wave function. Okay, so this is the original solution that these people worked out. So interestingly, there is a phase transition that appears because one can compute energies of of the two lowest states, and one observes that at one point they cross each other, and essentially they divide the phase diagram in two phases that can be physically thought in this form. There is for J small than this critical J, there is a pair state where all the fermions in the bulk tend to paired, and the impurity is essentially decoupled, and so this is the impurity is unscreened, and essentially we have a BCS ground state that is as usual a singlet state. On the other hand, when the Kondo coupling is larger than the critical value, there can be an additional fermion that can couple with impurity and essentially screen the impurity in the Kondo sense, and this leads to a non-BCS ground state which has half integer spin. Okay, so this is essentially the physics of this model. Okay, so these results were tested, numerically tested in this paper in '97. So essentially at the critical value, one observes that there is a jump in the spin polarization and in the order parameter, in the gap function, and that essentially there is this is the energy at the bound states. There is a change. There is a crossing, a level crossing at the point of the phase transition. So it's a well-known. I mean, it's a very well-studied model, and the results are known. The problem with this solution. Okay, so let me just complete the picture of this problem. There were experiments. The first experiments were made in '97. So essentially, they studied the differential conductance in a series of samples, and in the cases where the atoms are magnetic, such as manganesium and gallium, and there is a feature at essentially 0 voltage, like there, and for non-magnetic atoms like silver, there is no feature at all in this differential conductance. So this essentially is consistent with the physics of the Shiba model. So, but these very early experiments were lately continued with higher technological possibilities, and the most recent one is from last year, where they use other type of materials to try to compare things from more quantitatively with the results of these impurity problems. So you see that to understand how to this sort of impurity problems is like a building block in order to study more sophisticated things, like many of them. So our intention in this work was at first to study the chain of magnetic impurities on top of a superconductor, and use techniques like bosonizations to study that, but very soon we realized that that was a very difficult problem. Yes? Yes. Yes. Yes, yes. Okay, so that's the thing. I mean, if you want to study the 1D chain of atomic of magnetic impurities, you can say, okay, I will try to understand the one impurity first. So, okay, the physics is like this. If you have one impurity in a superconductor, then you have a zero energy, or not a zero energy, an interband, subband state. So the hope is that if you put many, this subband state will form some kind of band, and in this band you will be able to find some topological form, Majorana states, and so on. So the path is start by the one impurity case and then trying to understand the many impurity cases. So at first we tried the many impurity cases. We realized that there were many things that we didn't understand, and so we came back to the one impurity case in bosonization and try to study it. So that's what I'm going to tell you now. So to study the one impurity in a superconducting bulk, the first thing one has to do is to try to reduce the original three-dimensional problem to a one-dimensional problem. If one wants to use bosonization, then one needs a 1D. And that can be done, this is a very common approach, that can be done but by expanding all our three-dimensional objects in terms of spherical basis, in the spherical harmonics. So one can expand the gap if there is a complicated gap, the fermion, the energy dispersion, and if one sits in the case where the superconductor is only as wave, then one managed to completely decouple all the terms with high L, and only keep the L equal to 0 contribution, which is what I wrote here. So here, this is the general three-dimensional kinetic energy, and after this decomposition, one only keeps the L equal to 0 contribution. One does the same for the superconductor, and only keeps the L equal to 0 contribution. And what is nice, or what allows to do this, is the fact that the condo term is only an L equal to 0 contribution. So there are no higher L contributions from the condo term. So essentially the system decouples into a three-dimensional minus epsilon superconductor, standard BCS superconductor, plus a one-dimensional impurity in a superconductor. And this is the model that we will study next. Okay, so the treatment of this model is quite, this is standard in one dimension. When one wants to study low energy excitation, so the first thing to do is to linearize the energy dispersion around the Fermi points. And in principle, we will have two fermions, one for the right branch and another one for the left branch. But one has to be careful, because since k here is a radial variable, so we are not integrating here as usually done between minus infinity and infinity, but only from the origin. So it introduces some boundary conditions, like and allows to extend things to the negative axis. Okay, so one can do it by defining the fermions in the negative region in this way, and if one does that, then the Hamiltonian takes this form. Essentially, we have now extended our integration domain to the whole space, and we have right movers and left movers. But observe that the right movers have spin down, and the left movers have spin up. So there are two components missing there as a consequence of the fact that we are originally dealing with half of the space. This is quite common in the treatment of the Kondo model. In the Kondo model, essentially, one only has typically just one chiral fermion, let's say the right one, and one has the right mover with spin up or spin down. One can do the same here, but if one takes that basis, then the pairing term looks much more ugly, and so we chose this basis to express things. So the pairing terms in this language takes this form, and okay, so the Kondo term I didn't expand it, but essentially can be written as this object there. Okay, so next one picks this Hamiltonian and applies the bosonization technique. The bosonization technique is an analytical technique that essentially is a mapping from a fermionic Hilbert space to a bosonic Hilbert space. So to apply to a model, so it's an exact mapping. So there's nothing that we are approximating there if our starting point is the correct one, and that starting point is essentially to have an infinite number of fermions that in terms of which write our theory. So first, we define a series of operators in this way. They are bilinear combinations of these fermions, and the two important points that allow for this mapping are these two. First, the operators that one constructed there essentially satisfy the bosonic commutation relations. And second, these bosons allow to expand, to construct the full Hilbert space of excitations. So if one picks, let's say, a Fermi level, a Fermi C with some fermions on top of it, one can create, let's say, a complex state in the fermionic Hilbert space. Okay, so these complex states can be completely reproduced by using some function of this bosonic operator instead of the fermionic ones. So that's all the magic. And once one have this mapping, one can extend it to map more sophisticated operators like the fermionic operator that can be written as an exponential of a bosonic field. The density, the fermionic density, that can be written as a derivative of this bosonic field. And terms like the Hamiltonian, this is a typical term in the Hamiltonian. We have fermion times the derivative of a fermion, and this maps onto a derivative of a bosonic field 2 square. However, the interesting thing in bosonization is that since the fermionic density writes as a linear object in the bosonic field, if one has interaction terms in the Hamiltonian that are quartic in the fermions, then they will appear as quadratic in the bosons. So in principle, we'll be able to solve it. Okay, these bosons defined here essentially satisfy a Katz-Moody algebra, and to put it in a more usual form, one can define these two dual fields over here that will satisfy canonical commutation relations. So they behave as a coordinates and in its conjugate momentum. So in terms of them, we write our Hamiltonian. We will have this H naught that essentially represents the kinetic energy. We have here, this is nothing but the Hamiltonian for a wave. We have the derivative of phi square and this other term. This term can be thought as the pi square term, so essentially it's the p square of typical Hamiltonian. The superconducting term writes as the cosine of 2 theta. And we have the two contributions of the Kondo Hamiltonian that write as this derivative of theta at the origin times the z component of the localized spin and the perpendicular component that is more involved because it writes as an exponential of phi times the s plus minus components of the localized spin. So these sort of things are having studied in the literature separately. For example, there are some papers by Luther and Emery from the 90s and Chimiao Si and Gaby Kotliar, where they studied the Kondo model, but in absence of superconductivity. And typically in that case, there are some tricks that can we implement to get rid of this, either of this phase here or either of completely this term there. So I will not implement them here because they are not totally useful here because I have this pairing contribution. If I try to get rid of this parallel contribution or if I try to get rid of this exponential here, then I complicate a lot the pairing contribution, so it's useless. Yes? Yes. Yes. This is sine Gordon. Okay. Conformal dimension. Yes, it's relevant, yes. Totally relevant. Okay, that's another route I could implement here. Try to do some RG, but I will not do that. So I will follow a different route. Before that, I want you to check these relations. I will be interested in computing the spin, the electronic spin, because it tells me things about the typical ground state I will obtain and be able to compare with the standard Shiba solution. And this electronic spin can be written as some kind of topological object in the sense that it depends on this field theta, but only at the very extremes of the space. Okay, so what we will do is to try to do some classical analysis. Okay, obtain classical equation of motions, and even though this is a very simple model, it turns out that the classical equations of motion are quite funny. Let me start by the case in the absence of the impurity first, and to add these constants there that I can just simply put them to 1, but in other situations, like if one goes to one dimension or add interaction and so on, they can appear there. So I will just put them there to see what happens. So this model, in absence of the coupling with the impurities, the sine Gordon model, it's a very well-known model, and one can think what to do with it because it's known that it's an integrable model. The Bethe ansatz solution is known. One can compute form factors. Okay, so one can do a lot of things with this model, but just with this model. If I add Kondo terms, then I'm lost. So I will not do that. Instead, I will pick the classical equations of motion. So these are the equations of motion, are known as the Sine-Gordon equations. One can think that there is a potential here that is essentially cosine of 2 theta, and so it represents a series of maxima and minima. And we can try to obtain the static solutions of these equations. If I neglect the time derivative, then I will have homogeneous constant solutions. For example, if theta takes the value n pi over 2, then since it's constant, the space derivative vanishes, and the sign also vanishes because they are special values. So essentially, they represent the ground state of my problem. I can compute the spin using this expression, and since it's constant, this gives 0, essentially. Okay. These are not the only solutions of the static Sine-Gordon equation. There are also solitons that takes this form and that behave. This is a plot of these kinks or solitons, and these are very localized objects that connect two minima of the potential. They can go from, for example, minus pi over 2 to pi over 2 to 3 pi over 2. Essentially, go from one of the minima to another one. And in the context of the theory I am analyzing, they represent Bogoliubov excitations on top of the BCS ground state. Okay, so what happens now if I add my impurity? I can again obtain my classical equations, and now we will have an additional term that is this one here. Essentially, it's a delta function. Sorry, it's not. It's evaluated in delta prime of x. They are not 0. Okay, and so this will divide my space into pieces and will introduce very specific gluing conditions at the origin. This delta 0 here is very much the phase shift that one computed that one can compute in the original fermionic version of the problem. So one has gluing conditions. Due to the presence of this delta function here, one can express the theta field as a sum of a Heaviside function plus some continuous function with continuous derivative. Okay, so this form will satisfy all the gluing conditions that one can extract from this equation. And so once one have this expression for the solution, okay, one can look at the right side of space and the left side of space. In those pieces, this term essentially vanishes since it's only non-vanishing at the origin. And to the right and to the left of the origin, one have soliton-like or kink-like solutions that one has to glue in the origin according to these conditions. The gluing conditions, one can apply them and gives rise to this expression. Look that just one comment. The Sine-Gordon equation is translational invariant. So one can add this x0 here that essentially does nothing since the translational invariance is guaranteed. But this problem is not translational invariant. So I can take advantage of that, and when I propose my equation, put some x0 there that I will fix by forcing the gluing conditions. So that's what happened. I mean, this equation should be read as an equation for x0, and something important here is that I always have the freedom to add 2 pi times an integer number to my solution. If I do it on the right and on the left, then I'm doing nothing essentially. But I can do it just on one of the sides. And if I do it in one of the sides, okay, then I have this term there that is 2 pi n. And since I have to satisfy this gluing equation, it restricts the values of the integer n that can be the values that n can take. So I obtained two kinds of solutions. If x0 turns out to be 0, then I obtain a solution that is it has a soliton-like form. It's not exactly a soliton because at the origin I have continuity of the function and derivative, but all the higher degree derivative are discontinuous. Yes. Okay. I'll come to that. And I can also have x0 negative, and in that case, the solution looks like a double soliton solution. It's nice because if one reads some standard books on the issue, like a Raman book, then it says very clearly that static equation cannot have a multi-soliton solution. The static equation can have one soliton solution, and just the dynamical equation is a place where appear more complex objects like multi-solitons or breeders or whatever. But okay, now in this case, double solitons appear in the static equation. And secondly, one can compute the topological charge of these solutions, and it turns out to give this number that is here, n/2. So, for example, if I restrict my values of the phase shift to move between 0 and 1, 0 and p/2, that is quite standard, then this number n can be either 0 or 1, and so this will represent solutions with 0 spin or half integer spin, and that's essentially what I'm looking for. So one important thing that I didn't mention is that if this term is not there, then the first thing one does is to look for homogeneous solution. There are homogeneous solutions of the pure Sine-Gordon equation, 2n pi/2 or whatever. But now these homogeneous solutions are not allowed. So the simplest solutions one can have are of this soliton type. Okay, so how, and coming back to your question, how do we identify the states? One can take the limit of the Kondo of the impurity coupling going to 0, and in that case, this term, this Heaviside function that we put there, goes away, and we can see that the n=0 solution, the solution with one soliton, essentially tends to a constant, and so we recover in this limit the BCS grand function. So that's what's going on. I mean, homogeneous solutions are forbidden. We have a more complex solution of solitonic type, but this is the solution that is representing now the BCS grand function. We have to keep in mind that we have an impurity somewhere, and it's not possible to have an homogeneous ground state. Okay, that's a good question. In principle, I mean, you can build. Let me first give a mathematical interpretation. You can give these solutions that just plugging one soliton in one side, another soliton in another side, and moving them. So the movement of your right and left solid. Um, so I don't have the answer for that. I don't know. The position of 10. Oh, sorry. No. The impurity is located at the origin. There is an interpretation one can. Okay, let me finish with this. So if one picks the other solution, the one that have two solitons, then in the limit of zero impurity coupling, it goes back to the standard soliton anti-soliton solution of the sine boron. So essentially we perform this map of presence of the impurity, absence of the impurity. Okay, maybe we can go in the direction you asked by looking at the spin density. One can pick the solution and compute the derivative, and it will give the electronic density spin profile. We have this term over here that comes from this continuity, and we have the second term that comes from the derivative of this function. So essentially, in one of the cases, we have this hyperbolic second over there, but with the singularity at the origin because of this shifting of the right and left side. So we see here spin accumulation around the impurity. We have also this delta function over there, but since this is not the total spin, this is an electronic spin, I have to add, if I want the total spin, the impurity spin, and the impurity spin will exactly cancel this term there. So this is the profile we get. If we go back to the other two solitonic solution, then it gives rise, since these two peaks tend to separate, gives rise to two peaks of accumulation of spin outside the origin. Actually, one can compute the energy of these two types of solutions, and one immediately convinced that this two solitonic solution has always higher energy than the one soliton. So this is essentially an excited state, and somehow one can regard that as sort of excitations due to some breaking of Coupe pairs around there that manage to create spin accumulations outside the impurity. But this is of much higher energy. So I will, if I want to plot a phase diagram, I have to concentrate on this type of solutions and analyze. Okay, now something I didn't mention. This is notice that this is a plus minus over there. So I can have this solution, or I can have another one that is an anti-soliton. Okay, so I have to look at those and neglect this one. Okay, then actually there is a phase transition. One can compute the energy of the kink and the anti-kink, single kink and anti-kink, and compute the energies and plot them as a function of this phase shift. And the energy actually crosses at exactly pi over 4. And that's very nice because pi over 4 was the exact value at which these two phases crossed in the original solution obtained by Shiba. So one can also compute the total spin of these two phases, and interestingly, one also goes from a phase of 0 spin to a phase of spin 1/2. So essentially, we are recovering this solution of Shiba and its phase transition in this simple mode. So again, our idea is this is like a first step in a long road where our let's say objective is to study quantum version of the model and many impurity chains. So, but this is a starting point. Another thing one can do in this very simple context is to directly deal with one-dimensional system. I mean, one can put a one-dimensional superconductor, the impurity on top of it, and add interactions in the superconductor. Interactions in, okay. Okay. Sorry. Okay, then I will go fast. This bosonization allows me to obtain, I mean, it's free to deal with these interactions, and it's just that I obtain a more involved Hamiltonian. Now I have spin-charge separation, I have charge degrees of freedom and spin degrees of freedom, and that's why I have two types of fields over there that couple in the superconducting term. And in this case, one can also pick the classical equations of motion, but now they are more complicated. If one forgets, for the moment, this impurity term, then of course one always have the constant solutions. One has constant solutions in one of the field and solitonic solutions in another one of the field. That means, I mean, if one looks this as a Newtonian particle in a two-dimensional potential, then constant solutions essentially are the maxima of this potential, and the solitonic one are solutions that connect to maxima. But from one maxima to another, I can do it along the axis, or I can do it following some diagonal. Okay, it turns out that the solutions, solitonic solutions along the axis, are quite simple, are the same type of solution I showed you for this for the three-dimensional case. But the diagonal solutions are not known in the general case, in which the Latinger constant Ks is different from Kc. The charge and spin Latinger parameters are different. So even though there is no analytical solution, there are approximations, and again, this solitonic type of approximation works very well. So just to finish, there is again, one can see again this nice phase transition. What I can mention from this is that the phase transition is located exactly at the same point as in the three-dimensional case, and it's not affected by the interactions. So the Latinger parameters do not move these crossing points of energies in the phase diagram. Okay, so I think I will finish here and just flash the conclusions to allow for some questions. Thank you very much.